Hello again, this is Mark Summers from Summers Technical Services. I was going to do a video here to go over the Solidworks simulation we're going to do for Project 01 and go through the steps. The idea, you'll be doing your hand calculations to calculate those values on the spreadsheet. You'll enter those numbers in the spreadsheet and I can check those as usual, but what you want to also do is run this simulation to be able to check the numbers, and you can verify that you've done your calculations correct by checking the numbers on the stress analysis you can do on SolidWorks simulation. So first thing I want to talk about is adding a material. We've got materials we can use that are already built into SolidWorks. The problem with these materials is they're read-only. I can't modify these materials, and sometimes they don't match exactly what I want. So we've got some aluminum alloys. You can pick one that's close to what you've got. And under steel, where is it? Steel up here. We don't have any A500, ASTM A500 steel, doesn't look like, but we'll find one that's close to start with, and then we'll edit it to add the real materials as per the handout I gave everybody for the material properties. You'll also notice on these SolidWorks materials that come with SolidWorks, these are all dimmed out. I can't edit any of these numbers. And so that's why I can't use these, because I want to edit some of these numbers to tune them to exactly what my material properties are. So we're going to make a copy of this, make it so that we can read and write to it, and we can change these numbers. So let's show you how to do that. First thing I'm going to do is come down here and go to the bottom. I've already got some libraries in here I've created, and I'm going to set some new ones up so you can see how to do this on your computer. So just right click down here in the open space and say I want a new library, and I want to put this in my SolidWorks folders, not these program data, because these are all read-only folders. So I'm going to come back to my folder, which is going to be under users, mark, documents, Texas State, there's our class, there's project, and so I'm going to save this under project 1, and I'll just call it ENGR 3311 summer semester. So now I've got a new library down here that I can add things to, and they're on my folder that I have read-write access to. So I'm going to select that I just made, and I'm going to go in here and say I want a new category under that library, and the new category is going to be project 1, and you can make another category, call it project 2. In case you're doing project 2, you can put materials in there, make as many as you want. Now I'm going to go grab one of those materials, copy it, and paste it in here so I can edit those values. So I'm going to go back to SolidWorks materials. I've got 6061 T6, so I'm going to go make a copy of it. Come down here, right click, copy, and I'm just going to go back down to the folder category I made, and I'm just going to right click and say paste. And there it is. The only difference is now I've got access to change these numbers. So I'm going to rename this thing to get rid of this SS thing. Excuse me. So there's my name of material, and now I want to come in here. All of these are going to stay the same. I've got my von Mises model type name, and so here elastic modulus, in my case, I need to make this 10,000,000, 10 million psi. I need to find my tensile strength, and according to my material properties here that I gave everybody, the yield strength for my material, no, tensile strength. Tensile strength is 42,000. And the yield strength is pretty close to that number. My number was 35,000. So I got 35,000 yield strength. That matches. 42,000 tensile strength. That matches. And I got my Young's modulus of 10 million. And I'm also going to check this density, and that's pretty close to what I had, but the one I labeled 0975. So now those are exactly matching. Thermal expansion coefficient, not really part of what the analysis I'm doing. Hardening factor, I don't have any plasticity models. Poisson's ratio is okay just like it is. So I'm going to say apply, close. Select that, apply, close. So now that's assigned to this material, my model, and it lives now in my hard drive so I can change those values. If I ever want to edit it, I just say edit material, and there it is. This is the one in this new category. So that's how to do that. Now that I got my material set, I want to go through the steps of running the analysis. So I'm going to go start a new simulation, a new study. So I'll go to Simulation tab. If that's not on there, you need to load that. You need to go Tools, Add-ins, and then make sure you've checked the simulation add-in gets loaded. So simulation, I want to go New Study, and I want a static study. I want to give it a name. It seemed like a good name might be TSU-102- in my case 00-P01. All right, there we go. So I'll say okay. Now I've done that. I just keep answering questions going left to right. So now I'm in the tab over here. I'm in the simulation tab, and I want to apply material. Well, I've already applied the material to the model. So when I click apply material on the simulation, it's just going to say, hey, would you like to use this same material you've already applied to the model? And I'll say yes, apply, close. Next button is fixture advisor. This is where I'm going to add the boundary conditions at the bottom. This thing is fixed in the ground, so I'm going to say pull this down and say fixed geometry. It's fixed at the bottom. I'm going to zoom down here. You'll notice I've got this split faces. This is the ground line here. This is 3 inches below the ground line. For reasons we'll talk about in class, I've made this 3-inch offset here so we don't get artificially high stresses here, and so we'll discuss in the class why I'm doing this. But I want to grab these 4 faces. There's one. And the split faces, I've split this up so we can do the loading for the wind later. So I'm going to click all 4 of those faces. I'm not going to click this here because I don't want it to be fixed all the way up to the ground. I want it to be fixed below the ground. So I've got those 4 faces. I'll say OK. And I've added those fixtures. Now I'm going to add a load. So the next tab is, after fixtures, is external loads. I'm going to pull this down and say I need to add a force. And I've got 2 different forces to add. I've got a vertical load straight down on this thing. So I want to select that face, and you'll go to the spreadsheet. It'll tell you what load to put on there, and you're going to want to make sure you're in the correct units, and then just type in the number, in this case pounds, for that load, and I'm just going to put in 100. The number's different. I'm just typing in some number to put it on there. So put the number that's on the spreadsheet on the assignment, and then say OK, and you'll get that little indication on the tree here. It's got one force is going straight down with a 100-pound force. So now we need to figure out where to put this wind load. Well, the wind load is going to be blowing from the north, and so based on the sketch I gave you, I'm looking down from the top. This is the top view. This is north-south, and then this is east-west. So I want to have the wind blowing down in this direction, which happens to be in the plus Z direction. So I want the force blowing this way. And so I want to spin this around, so I'm looking at this back side here. And so I want to put that force on this face here, right there. I think that's it. So I'm going to space bar and look down from the top to make sure. So I've chosen the wrong side, right? I want the wind to blow from the north, and so I need to grab these other 2 faces here and here. So I selected the first one, control click the second one. Now I've got those 2 faces selected. Now if I look at the top, look down from the top, now I've got the correct side. I want that wind to blow from the north, and those are the 2 faces on that back side. Okay, so these are the 2 faces I want to add the load to. I'm only going to add them down to the top plane here, and so it's these 2 faces right here. So I'm going to come in here and I want to say external loads, want another force, and I pre-selected those faces, so it already chose those two faces that I want. And what you're going to do is you're going to, let me do an isometric view here. You're going to need to tell it that it's going not perpendicular to the surface. See how the force is going perpendicular to the surface? I need it to go in the Z plane because I want the wind to blow straight from the north to the south. So under direction, I'm not going to use normal because it's assuming I want to go perpendicular to that face. I'm going to choose selected direction, and I get another blue box here, and I'm going to use one of my planes, which happens to be this front plane, to define the direction. So this is a blue box. I want to select front plane, and I want to go perpendicular to that plane, which means I need to change this to English units. And I don't want per item, I just want the total for those two faces. Those two faces need to have a total load on there. And so I want it to be not parallel to that face, not vertical. I want it to be perpendicular to that face. I want the load to be normal to that plane. And now it's pointing in the correct way. If I look down from the top, those arrows are pointing from the north to the south, so that's in the right direction based on my selected direction, perpendicular. And here you got a value for PSI that you calculated using our equation to convert from wind speed in miles per hour to pounds per square foot. And then on the spreadsheet, I'm asking for pounds per square inch. But we're not putting in pounds per square inch, we're putting in pounds. So you'll multiply your pressure that you calculated, multiply by the projected area, which is a projected area when you're looking into that face, which means it's just going to be 360 inches tall by whatever the outside diameter of your tube is. So that area times your pressure will give you the value you need. And everybody's will be different, but I'm going to type in 1,000 pounds. You'll use your number there instead. So I'll say OK. And when I spin this around and look at it in isometric view, see how those loads are going perpendicular. They're going from the north to the south in the Z direction on those two faces. So now I've got my material defined. I've got my constraints, my boundary conditions defined. I've got my two forces on there. And now we'll do the mesh and then run the analysis. So I'm going to use this down. I'm going to create mesh. And I'm going to, for the first pass, I'm going to slide this slider over all the way to find and run it and see what kind of mesh I get. So I'm going to zoom in and look at this mesh. It looks pretty lame because it's pretty coarse up here. And I like to have two or three, hopefully three elements across this smallest face here. So I'm going to run this now and see what kind of results I get. Later on in class, I'll show you how to refine that mesh to get better answers. But for now, I'm going to leave it like that. And before I run it, I'm going to say File, Save As. I want to save it as the correct file name. And I want to call mine, you're going to name yours with your student number. I want to save it as 00 so that if the thing crashes, I don't want to copy results. Or I don't have any results, but I'll say yeah. Okay, so now I've saved it. Now I can run it. So I'm going to say run this study. And I can click on this. Or you're potentially going to get this warning message, excessive displacements. What happens when you have high displacements, the load direction could potentially change due to the deflection. Evidently, we've got enough deflection, where it's warning us that, hey, you might want to consider running large displacement calculations. And if we do that, it's going to go through this iterative process that I can talk about in class. But we're going to say, if you get this message, just say no. We're going to solve with small displacements, and that'll run quicker, and we can check our answers to see if it's a valid solution or not. So mine ran pretty quickly. So now I've got the results done, And again, I'll probably say file save, just so I don't lose anything. Now we need to go ask for the stresses at the base in those at points A, B, C, and D. So I've defined points A, B, C, and D on the on this model based on the handouts. So I'm going to do a spacebar, look down from the, or no, I'm not going to do a spacebar. I'm going to, first of all, turn off this deformed result thing. It shows it deformed, and I don't want to say it that way. I want to say it like this. So I've got to go ask for what I'm looking for. And so what I'm looking for is a normal stress on this face right here, this top plane. And the top plane is looking down. Here's the top plane. So what I want is, I want to ask for the right stress. And that plane, the top plane, where I want to calculate these stresses, is the Y face. See the Y axis here? Y is going straight up, so this is the Y face. So I'm going to select results, right click, and I'm going to say define stress plot. And I want to nicely ask SolidWorks to give me sigma Y, normal stress, the Y face. And I want the units in PSI in my case. And I say okay. Now it's plotting the normal stress everywhere in the model now. And this is what the legend tells me. And so again, I want to turn off this deform result. And I know the maximum stress is going to be here at the very bottom. And so what I'm going to do is I'm going to do a section cut right here at the bottom so I can probe it. And so to do that, just like we did on our other homework assignments earlier in the semester, I'm going to go to Plot Tools. First of all, I want to select this top plane. And drag this back over here. And go grab that top plane. I'm going to pre-select it. If I can find it. Top plane. Plot Tools. Section Clipping. And just say, okay, it's going to cut it right there, and I'm going to be looking into that face. Excuse me. And I'm going to look down from the top. And I'm looking down from the top. So based on the drawings we had, this is north, south, east, and west. This was point A at the top, and point B, point C, and point D. So I want to probe it and find the answers. These numbers are going to be different because I didn't have the correct lows, but you'll see what the plot tools look like. So I'm going to zoom in here and go Plot Tools, Probe, and I want to probe right there. And it tells me the XYZ location is X is 0, or pretty close. Y is 0, and Z is -3. This is right there at the bottom at the top. I'm going to come down here. I want to probe down here, and that's the same coordinates, except it's going to be +3 instead of -3, because plus Z is going down. And then I'll come over here, probe that point, and probe this point. This is the normal stress on the Y face due to that vertical normal force and due to the moments created by that wind load. So you'll check these values here for these solutions I've got here, and you're going to compare those against the values you got for sigma Y at point A, which is this one, point B, this was point C over here, and this is point D. So you'll do a screenshot of this to keep for your records, and also email me so I can be assured your numbers on your simulation match your numbers that you calculated on the spreadsheet. And this is how you'll earn credit for doing the simulation for Project 1. So I think that takes care of instructions you need for Project 1. If you have any more questions, stop by during office hours or shoot me an email. And we'll talk to you in class on Monday.